I'd like to talk today about how to calculate this curvature quantity that we've been interested in. If you'll remember, we're going to look at the unit tangent vector, t. We're going to think about how it changes as you travel along the curve. In fact, we're going to use the arc length parameter to describe the curve, and I'd like to know the magnitude of the derivative of t with respect to s. Working directly from the definition, this is not a very promising thing, but after we did much vector trickery, we found something out. We found out that if I do the cross product of acceleration and velocity and take the magnitude of that, divide that by the cube of the speed, that turns out to be this curvature quantity that we're interested in. Parenthetically, you might notice that's also the acceleration in the normal direction divided by the speed squared. As our first really concrete example of this sort of thing, I want to think about the curvature of a circle. I'm going to say that the radius of this circle is some number b, some positive number, and as we've seen before, I'll write a vector-valued function b cosine ti plus b sine tj plus 0 times k. I need to calculate the velocity vector and the acceleration vector, both of which are straightforward. When I do the cross product of a and v, if I'm clever, I'll make this observation. Both v and a lie in the xy plane. The cross product of them is at right angles to the xy plane, so for this particular circumstance, I already know that only the z component part is going to amount to anything. If you like, you can write out the other two determinants, but you find out that they're zero. We do have to calculate this determinant, though. Being careful with grouping symbols as not to mess any signs up, we found out that this determinant actually is the negative of the number b squared. A cross v is the negative of b squared multiplied by the vector k, the third of my three basis vectors. The magnitude will be the absolute value of this number, absolute value of b squared, times the length of the k vector, which is 1. B squared is positive, so to get the absolute value, I just drop the minus sign. We also need to know the speed, but that's just the magnitude of the velocity vector. A very similar calculation reveals that the speed here is equal to b. According to what we said previously, the curvature is the magnitude of a cross v divided by the speed cubed. That would be b squared over b cubed, which is 1 divided by b. At every point on a circle of radius b, the curvature is the same, and it is the reciprocal of the radius of the circle. If I want to make physics connections to things, in our formula for the acceleration as a combination of t and n, we already know something about the a sub t. It's the second derivative of distance traveled with respect to time. This other thing, the acceleration in the normal direction, one way to write it is the speed squared times the curvature. Many people will make up another variable, which is the reciprocal of the curvature. So if I use cursive r to mean 1 over the curvature, this says that the acceleration is this, which we have a nice physical interpretation of, plus n is a vector of length 1, and this is speed squared divided by radius. If you think back to when we looked at motion in a circle, the acceleration, if you're moving at constant speed, is speed squared divided by the radius. So for that reason, people sometimes write this equation in this form, where cursive r is called the radius of curvature. I want to think about curvature in terms of the situation that you found yourself back in the first semester of calculus. We had graphs that looked like y equals f of x, and I'd like to calculate the curvature of this. The easiest way to think of this is this. If I told you what x was, that would tell you what the y is. That means x determines everything about my function. X ought to be the parameter. So for t, I'm going to use the x variable. Y, which is f of x, then will just be f of t. My position vector is x times the I vector. That would be t times the I vector, plus f of x, y, f of t, that is, times the j vector. And since I'm going to be in the two-dimensional plane, 0 in the z direction. If you calculate the velocity, which is the derivative of position, derivative of t is 1, derivative of f of t is f prime of t, the acceleration is the derivative of the velocity, derivative of a constant is 0, derivative of f prime is f double prime, and the derivative of a constant is 0. I'll also need to know what the speed is. The speed is the square root of what you get when you take the components of the velocity vector, square them, and add them up. In this case, the third component was 0, so we just end up with 1 plus the square of the derivative of f evaluated at t. T is, of course, secretly x here. Just as before, both the velocity and accelerations lie in the xy plane. The cross product must be parallel to the z-axis, so I'll just be lazy and only write down the third chunk. When you do the determinant, you get the negative of the second derivative of f evaluated at t multiplied by the k vector. Now, the negative sign doesn't really tell me anything. F double prime could be negative, in which case the negative of it would be positive. F double prime could be positive, in which case the negative of it would be negative. The magnitude is the size of this number times the length of the k vector. So I'll put absolute value f double prime at t times 1, which I won't bother writing down. So writing my formula down, I write my absolute value of f double prime upstairs. Downstairs, I have to have the cube of the speed, which we previously figured out. So the curvature is going to be given by this formula. To translate this back into what we're used to, remember that t and x are the same thing. Also, f of x is the same thing as y. The curvature is the absolute value of the second derivative of y with respect to x over the 3/2 power of 1 plus dy dx squared. So if we have a graph of the type we studied back in Calculus 1, we can easily turn it into something like this and calculate the curvature. Now that we know that, it's easy, for instance, to calculate the curvature of y equals x squared. dy dx is 2x, the second derivative is 2. Curvature is absolute value of 2 divided by the 3/2 power of 1 plus the square of 2x. Absolute of 2 is 2. 2x multiplied by itself is 4 times x squared. This is the curvature at a given point on y equal f of x when you know the x coordinate. This curvature business may still seem kind of mysterious, so I want to use that previous result to back up a little bit. Imagine you've got some graph, y equal f of x. At some point p, there is a tangent line. The slope of that tangent line is equal to the value of dy dx. On the other hand, if you're on that tangent line and you went delta x sideways and delta y in the up and down direction, divide delta y by delta x, that will be the slope of that straight line. But horizontal on the bottom, vertical up and down, that's the tangent of the angle that the tangent direction of the curve makes with the horizontal. So I'm going to call that angle theta. Naturally, as you move around on the curve, the steepness of the tangent line changes, theta will change, and I want to think about how exactly does theta change, and in terms of what variable. So tangent of theta is always the same thing as the value of the derivative. This is true at each point of the graph. Theta will change, dy dx will change also. Take the derivative of both sides with respect to x. Over on this side, we'll have the derivative with respect to x of dy dx. We'll have the second derivative of y with respect to x. Over on this side, I have to use the chain rule. The derivative of tangent is secant squared. Evaluate that at the same place you were evaluating the tangent at, and multiply by the derivative of theta with respect to x. We have a trig identity that says secant squared is 1 plus tangent squared, so I'll go on and write it that way. If I divide both sides by 1 plus tangent squared, I find out that the rate at which the angle of inclination changes with respect to the x variable is the second derivative of y with respect to x over 1 plus tangent squared of theta, but tangent of theta is dy dx. So the rate of change of theta with respect to changes in the x coordinate is the second derivative of y over something that should seem vaguely familiar to us. So I'll use the chain rule again. D theta dx is the same thing as d theta ds, arc length, times ds dx. This is the chain rule. If you remember from 1920, in the y equals f of x situation, the derivative of s with respect to x is square root of 1 plus dy dx squared. This tells me that d theta ds times that radical is the second derivative of y over this quantity on the bottom is the same as this, except it doesn't have a radical on it. If I divide through by the square root, I find out that d theta ds is the second derivative of y with respect to x divided by the 3/2 power of 1 plus dy dx squared. But if you look at that, look at the thing over on the right-hand side, we figured out that the curvature is that same thing, except we don't have the absolute value on it. Except maybe for a sine. This is the curvature. And what's the curvature? It's literally the rate at which the angle of inclination is changing with respect to arc length. It's literally the rate of change of direction with respect to arc length, which is how we were thinking about it previously anyway. Another common situation is to have x variable that's some function of t, y is also a function of t, and we would like to find the curvature. There are two commonly used notations for derivatives. There's the dx dt, dy dt, second derivative symbols. Those were primarily due to Gottfried Leibniz, but Isaac Newton didn't write things that way. When Newton wanted to write dx dt, he would write an x with a little dot above it. And similarly for dy dt, he would write second derivative of x with respect to t as x with two little dots above it, and likewise for y. Some people haven't seen this kind of notation before, so I think I'll use this as an excuse to work with it a little bit. So my position vector now is going to be x of ti plus y of tj plus 0k. We are still down in the xy plane here. Using the dot notation, I can write down what the velocity vector and the acceleration vector are. A cross v will be found by using the usual determinant. Just like before, all but the z component ends up being 0. If you don't believe it, go on and calculate the x and y components, and you'll see that they're 0. After knocking out the row and column that has the k vector in it, I'll have this determinant, x dot times y double dot minus y dot times x double dot. The magnitude of a cross v is the absolute value of this number multiplied by the length of vector k, which is 1. So the top of my fraction in my curvature formula is this. Calculating the velocity as before, and then taking its magnitude to get the speed, we found out that the speed is the 1/2 power of x dot squared plus y dot squared. So I have to have the cube of the speed in the denominator. As a result, the curvature is given by this formula. For example, suppose that the x-coordinate were t cubed plus t plus 1, and y was t squared plus 5t plus 2. Let's say I want to find the curvature on this pathway at the place where t is equal to 1. I'm going to need to know first and second derivatives of both x and y. If x is t cubed plus t plus 1, the derivative is 3t squared plus 1, and the second derivative is 6 times t. On the other hand, if y is t squared plus 5t plus 2, the derivative of y with respect to t is 2t plus 5, and the second derivative is the constant value 2. At the moment that I'm interested in, x dot will be 3 times 1 squared plus 1, which is 4. At t equal 1, x double dot is 6 times 1, which is 6. Y dot is 2 times t plus 5. That will be 2 times 1 plus 5, which is 7. And y double dot is always 2. I know all of the little pieces I need in order to write down the curvature. So writing the numbers in, taking the absolute value, cubing the speed, the curvature is 34 over the 3/2 power of 65. If you wanted, you could then turn that into a decimal number. In this discussion, what we've found out is how to calculate curvature in several different scenarios, and more importantly, I think, a very explicit meaning to this curvature. It is literally the rate of change of the direction of the curve as you travel along the curve. These are the things that I wanted to get across in this video, so I'm going to stop there for today. I'll look forward to seeing all of you again real soon, and I hope you have a good day.